Okay, well, thank you for your kind presentation. Ladies and gentlemen, good afternoon. My name is Andrea Zanichelli, and today I'd like to present you a paper which is related to the fatigue life estimation of additively manufactured metals. First of all, I really would like to thank my co-authors from the University of Parma in Italy. So the present research work deals with the proposal of an analytical methodology for the fatigue life estimation of additively manufactured metals, which are subjected to cyclic loading, and in particular, an experimental campaign which was taken from the literature is considered and satisfactory results are obtained in terms of fatigue life. And this is regardless of both the specimen geometry and the degree of multi-axiality. So my presentation consists of the following sections. After a brief introduction related to additively manufactured metals, I will describe the analytical methodology proposed for the fatigue assessment of such materials, and even in the case of stress concentration. And then I will summarize the experimental campaign analyzed. And finally, I will show the results obtained in terms of fatigue life estimations for both the plane and notched components before moving on conclusions. So very briefly, as is well known, additively manufacturing is characterized by many advantages with respect to the traditional manufacturing techniques, and we can just briefly mention the realization of customized structural components and the considerable low material waste. But although the many desirable features, the AM field is still characterized by several open challenges related to the uncertainty on the structural performance of these materials, especially under complex cyclic loadings typical of in-service conditions. So, for example, relatively to the fatigue performances of AM components, they appear to be reduced with respect to the case of the corresponding traditional metals, both in low and high cycle fatigue regimes. And this is mainly due to the internal defects, the residual stress, the surface roughness, and the material anisotropy that are all related to the specific manufacturing process. So in order to counteract the above disadvantages, the AM components can be subjected to some post-manufacturing treatments, that is sulfate treatments or heat treatments. And this is mainly in order to improve the surface finish and to introduce a superficial compressive residual stress, as well as to homogenize the material microstructure and to reduce the internal defects. So in this context, nowadays, the goal of the research is still to find and validate criteria for the fatigue assessment of AM metals. And in particular, critical plane-based criteria has been found to be in generally a valid tool to this aim. So in the present paper, an analytical methodology, which has been recently proposed by the present authors for traditional metallic components subjected to fretting fatigue, is extending it to the case of AM components, even in the presence of a stress concentration. So let me firstly describe to you this methodology, which is based on the joint application of a multi-axial stress-based fatigue criterion, exploiting the concept of the critical plane, that is the Carpinteri criterion, and a stress averaging method, that is a critical direction method. So in particular, the Carpinteri criterion is used to define the fatigue parameter as well as to perform the fatigue life assessment of the component, whereas the critical direction method is employed for the determination of the critical plane orientation. Moreover, this methodology takes into account a parameter which is related to the material microstructure, that is the average grain size of the material, which is named here D. So here are shown the main steps of this methodology in the case of metallic structures with stress concentrations. And in particular, firstly, some input data need to be set, that is the geometric sizes characterizing the notched component, the loading conditions, and the mechanical and fatigue properties of the material. Then the stress field is computed within the structural component, and the hotspot location is defined on the surface of the component itself. That is, the crack nucleation location is defined. After that, the critical plane orientation is determined by employing a procedure which is based on the critical direction method. And finally, the fatigue assessment is performed by employing the Carpinteri criterion. So relatively to the determination of the critical plane orientation, well, once the hotspot is defined on the material surface, different material planes are considered, and these material planes are passes through the hotspot and are characterized by an orientation alpha. So firstly, a proper angular increment delta alpha needs to be set, and then an initial value of alpha equal to 0 is assumed, that is an initial critical plane candidate is considered. And in particular, this critical plane candidate is represented by a segment which starts at the hotspot and move inward to the structural component up to a length equal to twice d. So then both the amplitude and the mean value of the normal stress component acting on the corresponding plane are computed in many equally spaced points belonging to the segment, as you can see in the figure. And then they are averaged, and their averaged values that are NA and NM overlined are employed to compute the fatigue parameter and equivalent A, which is given by the equation shown here according to the Carpinteri criterion. So then a new material plane is considered, and this procedure is iterated for all the material planes inward the structural component. So finally, the orientation alpha critical, which maximizes the bow fatigue parameter, is assumed to be the critical plane orientation. Well, once the critical plane orientation has been defined, so the fatigue assessment follows, and it is performed by employing the stress components acting on the critical plane itself at the verification point P critical, which is located here at the end of the segment representing the critical plane, that is at a distance from the hotspot equal to twice d. And the fatigue life is computed according to the Carpinteri criterion by iteratively solving the equation shown in the slide. So finally, it is important to highlight that in case of plane specimens without notches, the critical direction method is not applied. As a matter of fact, the critical plane orientation in this case is determined according to the original formulation of the Carpinteri criterion. And moreover, the verification point coincides with the hotspot on the material surface. So let me now briefly describe the experimental campaign used for the verification of the proposed methodology. In particular, we consider the experimental campaign carried out by Wang et al. On additively manufactured AISI 316L stainless steel, subjected to cyclic loading. And during this experimental campaign, the selective laser melting technology was used, and a post-manufacturing heat treatment was performed. So then each specimen was machined from the EM annealed rods by means of a conventional lathe in order to guarantee the same surface finish to all the specimens. And in particular, as you can see in the figure on the right, 4 different specimen types were manufactured. That is a plain specimen and 3 different notched specimen characterized by sharp, circular, and blunt notches. Then each specimen type was subjected to pure axial, pure torsional, and biaxial fatigue tests. Relatively to the biaxial fatigue tests, both in phase and out of phase configurations were tested, and then the tests were characterized by a fatigue loading ratio equal to either 0 or -1, and finally different stress levels were considered for each loading configurations. So let us move to the results. Here in the present slide, the results in terms of fatigue life, calculated fatigue life versus experimental fatigue life are shown for the plain specimens types. And in particular, it can be observed that all the results fall within the scatter band 2, which is the dashed lines in the present graph, for both axial and torsional fatigue tests. And whereas for biaxial tests, the results are within the scatter band 3. with the only exception of this value, which is related to loading ratio -1 and phase angle equal to 90 degrees, which is at least on the conservative side of the graph. So in order to see the accuracy of the results we obtained, we can use the root mean square error method. So we obtained actually a TRMS value lower than 2 for both axial and torsional fatigue loading, whereas in the case of biaxial fatigue tests, we have a TRMS value slightly higher than 3, but let me say that in this case, statistical considerations are quite unreliable due to the very low number of specimens tested for each loading configuration. And here you can see the same results for the notched specimens. In particular, also in this case, quite accurate results are obtained since almost all the results fall within scatter band 3. And this holding true irrespective of the loading configurations. So it can be highlighted that TRMS value approximately equal to 2 has been obtained for both blunt and circular notched fatigue tests, whereas in the case of sharp notch, a quite higher value has been obtained. So as a matter of fact, the level of accuracy that we have obtained in the case of blunt notch is exactly comparable with that related to plane fatigue specimens with which were characterized by an overall value of TRMS equal to 1.98. And now let us move to the conclusions. So in the present paper, an analytical methodology has been proposed for the fatigue life estimation of additively manufactured metals subjected to cyclic loading. And in particular, this methodology is based on the joint application of the Carpinteri criterion and the critical direction method, and it has been applied to an experimental campaign which was taken from the literature. And it was related to both plane and notched AEM stainless steel specimens. So it can be stated that a high level of accuracy has been obtained in terms of fatigue life assessment, at least for the case of the material considered. And with the overall TRMS values lower than 2 for both plane and blunt notched specimens, slightly higher than 2 for circular notched specimens, and with a higher value related to the sharp notched specimens, but still lower than 3. Moreover, the level of accuracy appears to be almost independent of the load configurations, and this is a very good point that confirms the robustness of the applied methodology, which is able to provide satisfactory results irrespective of both the loading type, the degree of multi-axiality, and the degree of non-proportionality. So thank you for your kind attention.
Okay, thank you for the presentation. There is time for one question. Okay.
Thank you for the presentation. It's necessary to comment this approach because this approach is appropriate for material like you selected, this 316L, because this material have the parallel lifetime curves in tension and torsion also. Yeah. In your approach, you use conventional fatigue limit, but this ratio between tension and torsion are different during the lifetime region in different type of material, which this line are not parallel. That is necessary to enlarge this approach for more general materials, not only for this, because this material seems to be conventional material, or this line seems to be conventional, but specific of additive manufacture is this non-conventional, not parallel line.
Yeah, yeah. Actually, well, in this case, we applied it to this material, but we already applied this procedure to many different material types in the field of fracturing fatigue. And actually, we take into account the two different slope of the SN curves in the here in the computation of the fatigue life, because as you see, the apex M and M star are the slope of the SN curve under normal and shear loading type. So actually, not for AEM metals, but for conventional metals, we are already applied to different type of materials, also with different slopes in the SN curves. Thank you again.
Thank you.